Today I will talk about representing matrices using algebraic ZX calculus. Okay, so first I will talk about the background and then the short introduction to algebraic ZX calculus, and then say how to represent the elementary matrices, and then some properties of elementary matrices diagrammatically. And finally, I will show how to represent any matrix of power size of power of 2 in ZX diagrams, and then really some very short where I will mention something I will do in the future. So first, so why do we want to represent the matrices using graphical calculus? There are a few reasons. First, there is a lot of redundancy in matrix calculations, so which could be avoided in graphical calculus. And second, matrix calculations always have all of the entries involved. In this sense, it can be seen as a global operation. But in graphical calculus, like ZX calculus, so the operations are basically diagrammatic rewriting. That means you only need to replace a part of the diagram by another sub-diagram according to a certain rewriting rule. So basically, this is a kind of a local operation. So this local operation can make things much easier than the global operation. And finally, the graphical calculus is more intuitive, and as a consequence, if you do rewriting to simplify diagrams, it's easier to find a pattern or a structure. So that's the reason I can think of why we want to use diagrams for matrices. Although matrices are already very successful in algebra. So why we use algebraic ZX calculus instead of the original ZX calculus? I mean, by like the first paper by Bob and Ross. So because so the basic reason, so I think it's very well written in John's paper, the ZX calculus for the working common computer scientist. So the original ZX calculus lacks a way to directly encode the complex numbers. So when you're going to represent matrices, it's natural to have a kind of extended version. So here, the version I used is the so-called algebraic ZX calculus, which can be seen as a kind of extended version of the original ZX. So we just needed, I will show later, so we just add some new generators, but not really extended, because the added generators can be expressed by the original generators, the green and red spiders. So, and also, we can still keep the powerfulness of the original ZX calculus. So that's why we use algebraic ZX calculus. And so now let me give a short introduction to algebraic ZX calculus. So the generators, as you can see, is also the green spider, but now it's labeled by any complex numbers, and also the identity and the harmonic, the swap, the cap and cup, and the triangle and its inverse. That's the generators. Oh, sorry. And also then the original spider is just the current spider which labeled by E to IR. And then the phase-free spider is just the green spider which labeled by 1. and this is the empty diagram, and this is the transpose of the triangle, and this is the inverse of triangle. And this is the tau is 0 and pi. So it can be defined. The red spider can be defined. And if I just use the faces 0 and pi, then it can be defined in this way. And also the AND gate in algebraic ZX calculus. Sorry, I just I read all the diagrams from top to bottom. So for the AND gate, so it's just a green spider and with legs, or the triangles leave the green spider, and on the top there is an inverse triangle. And this is just the transpose of the AND gate. And here this is just a green spider labeled by A, but with legs, the up legs operated by some triangles. So here, and then that means this is just the transpose of the AND gate, and this means this notation just means there is an AND gate and you plus a triangle and a green spider. So that's some useful short notations. So what does it mean? So what's the interpretation? The standard interpretation for the algebraic ZX diagrams. So like here, you can see the green spider now labeled by A is just here. You put A here, right? Times by A. So before it's just E to I alpha. Now it's just A. So here, this red spider is actually it's pink, right? So it's exactly the same. It's the same as the original red spider, but except for they up to some scalar. So now this you can see here, just the coefficient is just 1. All the coefficient is just 1. So now this is Hadamard node is unnormalized. So you can see there's no 1 over root of 2. So this, what is the triangle? This triangle is just a 2 by 2 matrix, which is all 1 except this is 0. And this is inverse, and this is the usual pi gate, and this identity, and the swap, the cap and cap and empty. And all the others, just the interpretation, all the diagrams are just their tensor, the usual tensor and the composition, the sequential composition. So the roots is here. I don't want to explain all of the roots. So yeah, the roots here. So like the fusion rule, and that's usually the usual one. But here just some roots involves the triangles. So like this symmetry of this big triangle, and this associativity, and this the single face can be copied. Okay, that's the roots. So yeah, that's a very short introduction to the algebraic ZX calculus. So now let's see how to represent elemental matrices. So what is elemental matrices? Everybody knows it, right? So elemental matrices, now here just consider the elemental matrices of size power of 2. That means because elemental matrices are always square matrices. So here power of 2 means the size is 2m times 2 to m. And so we all know that elemental matrices correspond to the elementary operations on matrices, right? If you do left multiplication by elementary matrix, that means you do elementary low operation, right? If you multiply the elementary matrices on the right, then that means you do elementary column operations. So totally there are 3 types of elementary matrices. So one is the row or column multiplication. So now here, if for example here, there is a 2 to m times 2 to m matrix, elementary matrix. So we count the rows from 0 to 2 to m minus 1. So this is the 0, and this is the i's, and this the i's, and this is the 2 to m minus 1. So if you times a for the i's row, then you got this for from it's from identity matrix. If you times A to the ith row or column, then you got this matrix. So this is the first type of elementary matrix called row or column multiplication. And also there's row or column addition. That means if you for the ith row, if you times A and then plus to the jth row, then you got this elementary matrix. Or if you see it as a column operation, then it is from the jth column times A to add to the ith column. And then row, the last type is row or column switching. That means you swap the ith and the jth row or ith and jth column. So that's the three types of the elementary matrices. And then how do we represent these matrices in? You can see these matrices are simple, right? So how do we represent them into the ZX diagrams? So first, for row multiplication, if you times for the ith row, you times A times the number A. This number could be 0. It doesn't matter. And then this matrix can be represented from top to bottom, represented by this diagram. So what does this diagram mean? That means here, so you put because it's 2m times 2m, so you got m wires, and here you count from 0 and k to m minus 1, and then you got m green node here, and there is a AND gate. You connect each green node to the AND gate, but labeled by a red face, which depends on the binary expansion of I. So here we write I in binary expansion is like this. AK is the sum of AK times 2k, right? So AK is belong to 2 and 2, 0 or 1. So here you take the complement of the AK bar, I call AK bar, then A times pi. So that means if this is 0, then if AK is 0, then its complement is 1. So that means you got a pi here. But if AK is 1, then complement is 0. Then you got a 0 here. 0, that means it's just identity. So this you label to the m minus 1. So m minus 1s you got m minus 1 bar pi. So you got these labels here, and then on the top, on the bottom, then if you multiply you multiply A, then you put A here. This is the green spider. You put A here, but just with one leg. Okay, so you can see it's a simple diagram, and so I give for the others. I want to give for here. I give a very short demonstration on how to derive it and how to prove it. So that means for the ith row, it can be written. You just check by basis, the standard basis, and for the ith row or the ith column, the standard basis corresponding to these states. Here from here to here. So you just plug in, and you do the copy, right? Do the copy. No matter it's 0 or pi, it can be copied by the green node. The copy, and then you got all the pi here. You got pi operate on the on the AND gate. Then you will get this scalar. This scalar is just A. This scalar just A. So basically, you got this you got this column, this vector, and this is exactly the ice column. So for the other input, you just got this just usual unit. So you can see, and then by standard basis, you can check this exactly the diagram which represents the elementary matrix. Okay, so there is a special case. That means if there's just one wire, if m equal to 1, then you can see the AND gate you can see as a you can just connect to have two wires and just connect to the same green node. Then you got this this diagram for m equal to 1. So I give you an example. So here, if I have a 8 by 8 matrix, so that means is m equal to 3, right? So for the second row, which means it is count from 0 for the second row, if I times 1/3, then this matrix is like this, right? And then because I count from 0, then this is 1. The I is equal to 1. So then its binary expansion is this. So that means you got the complement of A2 and A1 and 0 is 1, 1, 0. 1, 1, 0 means you hear 1 times pi is pi. 1 times pi pi. 0 times pi 0. So you got the disappeared. So this part you got pi 0. And here at the bottom is just times 1 over 3. So just put the 1/3 here. So that's the diagram for this elementary matrix. Okay, so and the next, so row addition. So row addition, that means for the second for the ith row, I times a to the jth row. So that means I need how do I represent it? Also, I use the binary expansion of I and j, both I and j. And so how do I do that? So that means if I do the binary expansion for both I and j, then there must be, because it's from I to j, so I and j should be different. So there must be some places in there some bit positions for I and j, they are different. So if I just use j1 to j's to denote the bit positions where the numbers I and j differ. So it's j1 to j's from 0, j1 to j's. So then how do we represent the diagram? So for the top part, top part is the same as the low multiplication. You have AND gate and you connect to each green node with a red node, which is also the complement of the coefficient of the binary expansion of I. So it's the same. But then at the bottom you put a triangle here, and then because it's times A, then you put A here, and this A connect to the different bit positions for I and j. So because it's j1 to j's, so you put A connect to each j. So A connect to j1, j2, and js. So that's the diagram for the row addition. So of course you can check by basis. So it's shown in the paper. I don't want to show you here. And there is also a special case if A is just one wire, and then the AND gate just the same. The two wires just connect to the same green node, and then you will get this one as a special case. Okay. Also, there's an example. So the example for from the ones row. From 1 row you times 2, add to the third row, actually, sorry, is the row 1 times 2 add to the plus to the row 3. So actually the fourth row, right? This is the second row. So this is the matrix, and so here m is equal to 3, and then the binary expansion for I is like this. Binary expansion for j is like this, and then that means they just, you can see they just differ at the second place. So it's j1, right? It's from j0 to j1, from j0, right? So it's j1. So j1 is equal to 1. So, and there's just one place they're different. So they're just s equal to 1. And then that means you connect them. And this is depends on the binary expansion of I. And this depends on the different binary, binary position. So it's just the j is to 1. This comes from 0. So it's here. So you can, this a is just, oh sorry, I forgot to put a 2. This is not a, this is just 2. This is 2, should be 2 here. Because now it's times 2. So now you can see this is a diagram for this elementary matrix. So okay, so the last one is the low switching and elementary matrix. This is the most complicated one. So here, so you just swap. So not exactly m big or equal than 2. So it can be m equal to 1. I will show later. So here, so you also, because you swap the i's and j's column or row, so you need the both of the as before, you need both of the binary expansion. So this is for I and this is for j, and they also the different at j1 until js, right? So it's here. So now how do you represent it? So then here, so you put at the bottom, at the top, you put all the green nodes on each wire. It's m wires. So all the green nodes on the top, and then there's AND gate. AND gate also connect to each green node, but they are labeled, each edge, each connection is labeled by a green. Is inserted by a red node. So the red node is a little bit complicated than is more complicated than the previous one. So for the wires which I and J's binary expansion, the bit positions are they are the same. The position when they're the same as this position, like 0 or for example here is 0 and m minus 1, then you don't need to do anything, just do it like before. You take the coefficient of I, and because it's the same as b, and then take the complement and times pi. But for the branches, for the lines we labeled by J1 or JKJS, then you should be careful. Then you should fix one. Here I fix J1, and then from JK, you need also to this red node. You need to connect both J1 and JK green nodes. You need to connect them, and the label is the complement of AJ1 plus is modulo 2 plus AJK, and then you take the complement and then you times pi. So should be careful. So here for this places where where I and j are different, for these bit positions, and I and j are different, then you should do like this. for the place where I and J are the same, and you should just do this. And then also they could just connect the AND gate just from the bottom connect to a green node, which the green node connect to those bit positions where ij are different. So it's J1 to JS. So that's the way how do you represent the row switching or column switching elementary matrix. So this one you can see is a little more complicated than the previous ones, but it's still okay, right? So let's see. So if the for the special case, if the there are some special cases because here if S is just one, then the connect should be to the same green node. So you got basically you got this diagram. And also if S is 2 but M is just 2 wires, and then you can see as we know before the swap is just the swap of I and J is just the usual swap. If M equal to 1, if M2 equal to 1, since the swap is I is not equal to J, so there's any one element matrix, right, for M equal to 1. So this you can see, then this just double. So the final one is just the pi gate, just pi gate. Okay, that's special case. And then example switch. Let's here also A by A matrix. If just from identity matrix, we just swap the second one, the rows 1, and the last one, the row 7. If we just swap these two, we got this matrix. And how do we represent them? So here, because M equal to 3, right? 2 to 3 is equal to 8. So M is 3, and same, the binary expansion of I is this, and binary expansion of J is this, and then you can compute the complementary coefficient for the binary expansion of I, and they are different at J1 and J2. And they're just different at these two places. So you can represent this diagram, this matrix at this diagram. Right? Okay, so that's now how do you represent all elementary matrices, all type of elementary matrices of size to power of 2 in string diagrams. Now. So how do we know this representation is good or is good at least? So actually we can show their properties, the properties of those elementary matrices by diagrams. So here we just show some simple properties like the inverse of the elementary matrices and the transpose of the elementary matrices. So for example, here first, so we have a non-zero complex number A, can be any A, non-zero. So we all know that the inverse, so if we multiply A to the isolo, then its inverse is just the multiply 1 over A, right? To the isolo, right? That means if they come together, they should be the identity, right? So how do we prove them? Then we use the diagram as we just showed. So this diagram for the low multiplication by A, and this is the diagram for the low multiplication by 1 over A. So yeah, you do this first on top and then this on the bottom. So you convert, that means you connect them, and when you connect them, then here we use because no matter it's 0 or pi, we can use the copy, right? They can be copied by the agreement. So copy. So let them move out of these connections, and then you got this diagram, and then now in the middle, all of these faces are cancelled out. They are the same, so they cancel out. They cancel out, then you have these two. And there's a property that for the AND gate, that means they can faces can added can be fused, and because now the fusion is a multiplication, then you got actually it's just when they fuse, it's just a green note here, just one. The coefficient is just one. And if we just coefficient is just one, then this can be disappeared to be identity. And once this become identity, then all of these faces this also cancel out. Then that means finally you get this identity. So and this part can be grouped similarly. So you can see once we have the diagrammatic representation of the low multiplication, then its inverse, the property of its inverse can be proved diagrammatically, and I think it's not the complicated one. Okay, so similarly, I just show one proof. If you are interested, you can see look at the paper for the details. So similarly, you can do all of this. You can check all this kind of properties by diagrams. So this low addition, the inverse of the low addition, and the inverse of the low switching, and then this is the transpose, and this is if you do first do times the isolope by b and then by a, then that means you times ab, right? Similarly, if times b to j and then times a to j, then that means you times a plus b to j, right? So these properties can all be checked by diagrams. Oh, so yeah, so now we have shown that the elementary matrices can all be represented by the diagrams, and the properties can be checked by those diagrams. Okay, and then finally, how do we represent any matrix of size 2 to m times 2 to n, right? So the strategy is simple. So giving an arbitrary matrix A of size 2 to m times 2 to n. So how do we draw it in diagrams? So first, we use the Gaussian elimination. So we turn A into a reduced low echelon form by means of a final sequence of elementary low operations, right? That's the Gaussian elimination. So we can then turn A into a reduced low echelon form. It's like this, right? Like this. And then for now, for the Gaussian elimination, we just use low operations, right? But for now, we can, if we also use the column elementary operations, then we can cancel out all these stars, right? It could be non-zero, right? Then we get this one. Then we use the swap. Then we can get this one, right? This is a kind of standard form. So here you got the identity matrix, which is of order R. R is the rank of A, right? So that's what we usually get in linear algebra. Okay, so the problem is, so now if we do this, if we turn this A into use a lot of elementary operations, both row or column, and turn it into a standard form like this, then if we need first to know how to represent this standard form, right? So how do we present this standard form? The idea is simple. So for example, so it depends on for operation, it depends on the shape of the standard form. So if m is less or equal than n, then we chop the standard form into blocks, right? We chop into blocks. So first is a k. K is a square matrix of size 2 to m times 2 to m, and then all the others are just 0. So we chop the C into blocks. Then what do we get? We get actually this tensor product is a row vector. It's a row vector. It's the first is 1, all the others are 0. So how many entries there is 2 to n minus n, and tensor with this k. Or what is the k? K is just this square matrix on the diagonal. On the diagonal, they're just elementary matrix of side of order R. So for this tensor to represent C, we just need to represent this tensor product. But this tensor product, for this tensor product, for the left part, it's just this, right? It's just this diagram, right? It's very easy. It's just a cat. It is braid 0, right? Tensors n to n minus n, braid 0, right? Just the tensor. And then we just, so this part is easy to represent. So K, how about K? So K you can see, and you can see this is just a diagonal matrix with all 1 and with R1s, and then all the other is just 0. So how this actually is as we can see is elementary. Is a composition of elementary matrices. So that means you can do the you can use the multiplication by multiplying 0, right? To all the on all the rows which has 0, right? It has 0. That means you just need to compose all of these kind of diagrams. Then you will get this K, the diagram for this K. So in this case, if n less or equal to n, then you can get a diagram representation for this standard form C. And similarly, if m is bigger than n, strictly bigger than n, then you chop in the other way, right? You chop the C in this way. So here you got K prime, so which is also a square matrix, but it's of size 2 to n times 2 to n, and then on for the bottom part is just 0. So it can be written as a column vector, is column unit vector, tensor with K prime with this matrix. Similarly, this one is just all the tensor product with this green dot, right? And this K prime can be represent the same way as K. That means you multiply the 0, right? For several times. It depends on how many zeros here. So that's the general way. So that's the general way you represent this standard form C. And in any case, we can represent the C by a ZX diagram, right? And since each elementary matrix can be represented by a ZX diagram, so if we from A to C, from A actually A to the standard form C, if we reverse procedures, then since we know how to represent C, how to represent any elementary matrices, because they're inverses or also elementary matrices. So then we know how to represent A, right? So, but in practice, that's a general method, right? But in practice, it's not necessary that you must go from the beginning to the last. That means if you can stop at anywhere. You know how to represent the diagrams. You don't need to. You don't need to go from here. even when you do the Gaussian elimination, if you can stop at where already know how to, if you for example, by observation, so you know how to represent them by diagram, then you reverse the procedures, then you will get the diagrammatic form of A. So in practice, it could be simpler. So now I give a very simple example for how do I do this. So let's consider actually 2 by 2 matrix. So it's A, B, C, D with 4 elements. Sorry. So A, B, C, D. So if X is just a 0 matrix, then it's very simple. You just put a pi, a scalar pi here, right, and with a straight line. But otherwise, we can assume A is non-zero. So if this is not the case, you can just do some switch. So we assume A is non-zero, and then we can let's do the operation, do the row operations. We times for the first row we times 1 over A, then we get this matrix, right? And then we want to cancel this C. Then that means from the first row we times minus C, then to the then add to the second row we got here, and here then we want to eliminate this element. Then we from the first column we times minus BOA to the second column. Then we got this diagonal matrix. So here we don't need to make it the standard form, right? Because we already know how to represent this diagonal matrix. It's just grins by the level by k. K is this element. So to represent the x, so you just you just need to reverse the elementary transformations. That means you do the column, you times before it's times minus BOA is now it's just times BOA. This is the column, and column put on top, and the row operations put on the bottom. That means you just need to do this. So then you can do the as we have shown before, you can for this elementary and transformations, you just use the diagrams put here, and then you do some simple simplification. Then finally you got this diagram for the matrix X, and this is a scalar. Basically, this means A, and then this diagram looks kind of symmetric, right? It's a green note, and then this big diagram, a bigger diagram like this, and then this one. But the coefficient here and here are different. So you can see this is a diagram for any 2 by 2 matrix with a non-zero. Okay, that's the way. How do we represent any any matrix of size power of 2? So what's next? So next we want to do mainly 2 things. One is that we want to represent some very useful matrix technologies, like which used a lot in tensor networks, like the single value decomposition, QR decomposition, and a lower upper decomposition using this technology. So by doing this, we hope we could pave the way towards visualizing important matrix technologies deployed in machine learning. And also, except for this matrix technology, so we also want to do to generalize the results to the QD and even Q-finite case. That means we want to represent. We don't want, although there is already a normal form for any finite dimensional vector. That means then you can, in principle, you can represent any higher dimensional J diagrams, any matrix. But we don't want to use the normal form for a vector. So we want to do do this in a way similar to we just showed. So this is also a future work to how to represent any finite matrix uh, relatively efficiently. Okay, I think that's it. Thank you very much.
Koughton is left, so there is no host of this meeting. So I suggest we just clap and thank Harney for the talk. Yeah, I guess I'll just take the role of Alex. Are there any questions for Harney?
Yeah. Do you know, so Harney, if you have sparse matrices, so matrices which have low numbers of non-zero elements, do you get a particularly nice form using the algebraic ZX?
It could be. It depends. So then yeah. So so the quite tricky thing is you need to how once you represent it, you also need to represent the sparse matrix by diagrams. You need to how do the problem is how do you simplify it as nicely as you can, right?
Mm-hmm.
Yeah, that's the tricky thing. You need then you need to should be very careful with the how to use the rewriting rules. Yeah, that's you can see that's the usual problem with that's the usual problem with
Sure. Yeah.
with index.
But it's not obvious that if you have a matrix which is zero almost everywhere, then a lot of the diagram will go away. Is that?
Yeah, of course they will go away. If there is a lot of zeros, they will go away. Yes.
I guess it's like if you have a sparse matrix, does it translate to a low amount of row and column operations? And I think there's some known results about that, like the amount of non-zero entries with respect to the size of the matrix. I think there's a ratio at which when you start doing elimination on it, then the number of operations kind of blow up because you kind of they kind of add on to each other and you get more operations than you think you would need.
Right. Yeah. So just being sparse, you have to have a good strategy for doing Gaussian elimination, I guess, which doesn't follow automatically from sparseness.
But but usually it's not necessary. But usually for a sparse matrix, when you do some Gaussian elimination, do some row or column operations, it's very usually you quite probably to find a way to make it into tensor products of some simpler matrix. That's usually happen sparse matrix.
So the target isn't always the identity. It could be a target, could be something else.
Yeah, as I've mentioned, yes. Yeah.
So Harney, if you apply this strategy to say synthesize an H-box or a matrix with ones everywhere except for one element in one position, do you get like a really big diagram because there's so many ones you need to add, or can you do some trick to still make it a small diagram?
Yeah, I do. Actually, I do try some. I do try some of this kind of matrix. I think for this kind of for all ones matrix, it could be simple, very simple. Because you use one after simplification, just one element right, on the diagram, right? So and then it's very simple diagram. It's very simple diagram, and then you do the low operations. Then it could be simplified quite a lot. Yeah, I do try something.
Yeah. I guess you can just start with a bunch of plus states, which gives you the state with there's ones everywhere. Then you do like a sort of CCZ-like thing. So kind of like one row operation to the element you want to change. Is what you get in your approach, I guess. But that sort of requires you to put this intelligence in there, that you want to start with like the all plus state.
4 plus states.
Yeah, so the state that has ones everywhere. Like if you just think about not a matrix, but as a state, right? Then to efficiently synthesize an H-box, you want to start with the state with the vector that has ones everywhere, which corresponds to like these green spiders that are not connected, like plus states everywhere.
Yeah.
And then you just do a single row operation to change the element you want to change.
Yeah.